All right, so this is section 4.8, antiderivatives and indefinite integrals. So we're going to go over the definition first. The definition says a function, capital F at x, is an antiderivative of the original function f of x on the interval I if we take the derivative of the antiderivative, and if that equals the original function for all x in that interval I. So what the antiderivative is? The antiderivative is the inverse operation of finding a derivative. So it's opposite. Okay, that's why it's called antiderivative. We're also going to call it integration. So if we look at this chart here, it says find the antiderivative f at x for all given for the original function f of x, and check to see if the derivative of the antiderivative equals the original function. Okay, so if the original function equals 2x, what would we have to have the original function be for that to be the derivative? And hopefully you said x squared. Okay, because if I do x squared, and if I take the derivative of that antiderivative, so if I take the derivative of x squared, we know that's going to equal 2x. So we get right back to the original value. Okay, so what I want you to do is pause me and fill out the rest of this chart, trying to figure out what's the original function. It'll give me this function back. And then I'm going to show you all the answers. So once again, please pause the video and do this chart by guessing. Okay. So I filled out this chart, and if we look at the second one, because we already went over the first one together, the second one says that we have the original function equals 3x squared. So the original function has to be x cubed, because when I take the derivative of x cubed, I get 3x squared, which matches up. For the next one, if the derivative is 1, what's the original function? It has to be 1x. So that's the antiderivative. So if I take the derivative of the antiderivative, or if I take the derivative of x, I get 1 back, so that checks out. This next one becomes a little bit trickier because I have x to the third. So if that's the derivative, I have to use x to the fourth. However, when I use x to the fourth, I'm going to get a 4 up front, right? Because when I take the derivative of x to the fourth, a 4 shows up. So that's why I put 1/4 x to the fourth as the original function, because once again, if I take the derivative, and you're going to see that in that work, I have 1/4 times 4 x to the third. So the 4's cancel out, and I'm left with x to the third. And then cosine. What gives me cosine? Sine x. So if I take the derivative of sine x, I get cosine x. And finally, the last one says cosine of 3x. Well, the original function has to be sine of 3x, but remember I have to use the chain rule on that when I take the derivative. So I made sure I put times 3 times 1/3. So to get rid of the 3, I'm going to have to multiply sine of 3x by 1/3. So if I take the derivative of that original function, which is 1/3 sine 3 of x, I get 1/3 cosine 3x times 3. And the 3 and the 1/3 multiply together to get cosine of 3x, which checks out. So all these check out. But once again, this isn't an exact formula. You know, this is guessing, basically. And before we actually start looking at, you know, the ways to do these, because trust me, there's rules for every single thing. We also have to talk about that when we have antiderivatives, we actually will have a family of antiderivatives. So for instance, if we have the function 3x squared, okay, and that's my original family, remember, if I take 3x squared and I add on any constant, and then I take the derivative of that, remember, I'm just going to get 6x out because the constant will drop off. So I can also do 3x plus 2. Same thing happens when I take the derivative of the function. It's going to be just 6x, etc. So we have to deal with this constant here. So when we deal with the constant here, what we do when we take and find the antiderivative is you're going to see we're going to tack on plus c onto everything. Okay? All right, so let's look at the bottom portion of this page. The bottom portion of the page gives a definition, and it says if the antiderivative for the original function f of x, then there's a general antiderivative for the function, and we write it out as capital G of x equals the antiderivative plus c, where c is a constant. Okay, now we're getting into the math terms. So this part is we're just looking at the math terms. So when we have to do an antiderivative and it has a family of functions, we're going to talk about taking the integral. So the indefinite integral means that we don't have any lower or upper limits that we're looking at. And you'll know the difference in the coming sections. But let's go over the pieces of this. So the integration sign is that thing that looks like an F hole of a violin. And then next to it is the integrand. And then we have the independent variable dx. So this is a variable in which we're taking the antiderivative. Okay? When we find that value, what we're getting out is capital F at x. That's the antiderivative plus c. Okay? So you always need the plus c when you find these answers. And furthermore, if I take the derivative of the antiderivative, I will get the original function back. Okay? And please note that the integral sign and dx are instructions only, and they cannot appear in your answer. Okay? So let's go ahead and look at it, the next example. Use the correct notation and variables for the following indefinite integrals. The integration of 3x squared. So if you look at the top of the page, we determined that if we take the integration of 3x squared, we get x cubed. So once again, if we have x cubed, remember we're going to tack on the plus c to that. Okay? The second one, 2x. So what will give me 2x? So if that's the derivative, how do I get that? Well, I know I have to do 1 power up, right? T squared. So if I take the derivative of t squared, I get 2t. So that checks out. But I need to put plus c there. And then the integral of cosine u du. Well, to get cosine, the original function has to be sine. And then, once again, we need the plus c. So don't forget to put plus c's on these because it's important. All right, so let's look at the next page. The next page is going to be your bread and butter for the test for test number 4 because it lists out every single antiderivative formula. I want you guys to notice that there aren't too many formulas that let us deal with products. So 8 and 9 have products, and I think that is it. So integrals, taking integrals of things are a little bit more challenging because we won't have any product or quotient rules. And when you take an integral, it has to match up with one of the rules exactly. And if it doesn't, then we have to do other things like algebra or try to make it look like one of these original functions. So once again, we're going to be going over these little by little, and I will be referring back to this page when I say, for instance, we're referring back to rule number 1. The integration of 1 dx equals x plus c. Okay, so let's go ahead and look at some things. Okay, by the way, the other part of this, and like I said, this page is your bread and butter. If we have a constant times a function, we can pop out the constant and just take the integral of the function. Also, if we have a polynomial that's showing some indifference of each term, we can break it up by taking the integration of each piece of it. And for these in functions involving f times k times x dx, you're just going to divide the antiderivative by k. All right, so we're going to see this all in action. And then at the bottom of the page, it deals with instances when we have something times x inside the parentheses. So for instance, the first one says the integral of cosine of kx dx. What do we do with that? We take the integration of cosine, which is going to give me back sine kx over k plus c. So this all deals with what happens when we have trigonometric functions that have kx or logarithmic functions that have kx as well. All right. And we also deal, if you remember, these last three on the bottom here are, the backwards derivative of inverse sine, inverse tangent, inverse secant. Okay, so like I said, we'll deal with these going through this section. So I'm going to move on. So we're going to look at example number 1. Find the general antiderivative. Okay, I see I have the function is given to me as x to the 5th. So instead of guessing what gives me x to the 5th back, I'm actually going to use the rule. So the rule that I'm going to use from page 2 is rule number 3. And rule number 3 says the integration of x to the n, sorry, hold on, I'm just trying to get this to work, is going to equal x to the n plus 1 all over n plus 1. And then we have to tack on the plus c. So let's see how this works. You have x to the 5th. So I'm going to add 1 to the power, and then I'm going to take that power and add 1 to it in the denominator. And then I'm going to have plus c. So this becomes x to the 6th all over 6, or we can write this out as 1/6 x to the 6th plus c. This is our answer. Okay, let's look at b. B says we have the square root of x. So I don't have any powers or any rules that say square root of x. So I'm going to rewrite x as x to the 1/2. So I'm going to take the integration of x to the 1/2 in terms of x. I'm going to use the same rule. So rule number 3. And rule number 3 again says the integration of x to the n dx equals x to the n plus 1 all over n plus 1 plus c. Okay, so let's go ahead and do this. I have x to the 1/2 power. I'm going to add 1 to that, and I'm going to throw it over 1/2 plus 1. So this becomes x to the 1/2 plus 2 over 2 when I find a common denominator over the same thing, 1/2 plus 2 over 2. So this becomes x to the 3/2 over 3/2. So when I make this look a little better, I get 2/3 x to the 3/2 plus c. So once again, with all of these, if you have an indefinite integral, you have to use the plus c. And finally, for part c, if we look at that, it's asking us to do something that looks more like a polynomial, sort of. We have 3x squared plus 5 over x squared. So I need to rewrite that because I don't have a rule that says how to deal with 5 over x squared. But I can rewrite this to look like this. Okay, so if I let that be my function and I want to take the integration of it in terms of x, so I'm going to use rule number 3 again. So once again, rule number 3 says x raised to the n. If I take the integration of that in terms of x, it's going to give me x to the n plus 1 all over n plus 1 plus c. Okay, so I'm going to do each little bitty piece. And by the way, if you have a coefficient like this 3 here, I'm going to kick it out. So basically, I'm going to integrate 3. I'm going to pop it out, take the integration of x squared dx. And then I'm going to also do the same thing with a 5. So I'm basically taking the coefficient off and putting it in front of the integration. Okay, so what do I get? So if I integrate x squared, I get 3 times x squared plus 1. So that's 2 plus 1 in the numerator over 2 plus 1 in the denominator. And then plus 5 times x to the negative 2 plus 1 all over negative 2 plus 1. And remember, we have to put plus c. So if I clean this up, I get 3 times x to the third over 3 plus 5 times x to the negative 1 over negative 1. Okay? We can see that these 3's will cancel each other out. And if they cancel each other out, I'm left with x to the third. And then the 5 times negative 1 is going to give me a negative 5. And then we have x to the negative 1 plus c. I'm going to rewrite this just one more time to get rid of the negative exponent. So I get x to the third minus 5 over x plus c is my answer. Okay, so we used rule number 3 several times for a, b, and c, and we saw how to handle something when we have a coefficient of a term. So if we have a coefficient, pop it out. Okay, D. Let's do D and E, and then I'm going to stop the recording. So for D, we have the function at x equals 2e to the x minus 5 cosine x. So what I'm going to do again is I'm going to take out the coefficient, and I'm going to take the integration of e to the x in terms of x. And then I'm going to pop out the 5, and then I'm going to take the integration of cosine x in terms of x. Okay, so we have to go back to our rule sheet and find the rules for these. So rule number 1, and I don't think that's number 1, but let me check my notes real quick because I don't think so. So if I look back on page 2, I'm looking for e to the x. So that's rule number 11. Okay, so rule number 11 says the integration of e to the x dx equals e to the x plus c. Okay, so this first piece is going to be 2 times e to the x. And then we're going to do 5 times, and we're going to look up the rule that deals with cosine. The rule that deals with cosine, if you look on this sheet, is rule number 4. So the integration of cosine x dx is equal to sine x plus c. So we get negative 5 times sine x, and then I'm going to tack on plus c. So making this look a little bit better, 2e to the x minus 5 sine x plus c. So that is my answer. Okay, and then let's look at e. So the original function says a function at theta equals 2/5 secant theta tangent theta. Once again, be very careful with these. If we have something that looks like a quotient, if we do not have a rule that looks like it, then we have to do some fancy footwork. But we luck out because there is a rule, and it is rule number 8 that says the integration of secant x, secant x tangent x dx equals, and hopefully you guys know this one, but it's secant x. Because remember, working backwards, plus c. Okay, so I'm going to kick out the 2/5. I'm going to take the integration of secant theta tangent theta, and that's going to equal 2/5 secant x plus c. And by the way, I should have a d theta because I am taking things in terms of theta. So let's just go ahead and make theta instead of x in our answer. Okay, so I'm going to stop the video and we're going to do another part. But that's how you do this page. So once again, I have to look up rules that match up what I'm asking to take the integration of.